Hi, everyone. First of all, I'd like to thank everyone for joining me today in this session. I'll be presenting a systems engineering approach to transient analysis in water distribution system using Bentley OpenFlows Hammer. My name is Neil Sipe, and I'm here to share my insights on how we can streamline the design, analysis, and optimization of water systems by integrating systems engineering principles using Bentley Hammer software. This presentation will highlight the significance of transient events, such as water hammer in water distribution systems, and demonstrate how a more structured approach to handling these events can lead to better designs and more resilient infrastructure. Over the next hour or so, I'll try to make it short. We will explore traditional approaches, the challenges they present, and how applying a systems engineering methodology offers a more holistic and efficient way to manage the complex interactions in water systems. Before we dive into the technical details, let me tell you a bit about myself. As I mentioned earlier, my name is Neil Sipe, and I am currently in the final year of my Bachelor of Engineering Systems at Southern Cross University on the Gold Coast, Queensland. I am also working part-time as an undergraduate civil engineer at SMEC, where my focus is on water infrastructure projects and water management and planning. Before I joined the civil engineering space, I already earned my master's and bachelor's degree in computer engineering. My background in IT and computer engineering have provided me with a foundation in systems thinking, data analysis, and modeling, skills that I found useful in the world of civil engineering. I have been fortunate to gain over 3 years of experience in civil engineering and applying these skills to a variety of water-related projects. My computer engineering experience has given me a unique perspective on problem solving and optimization, particularly in complex infrastructure systems like water distribution networks. I hope to bring that perspective to this presentation today. I would also like to take this opportunity to express my gratitude to the organizers and Systems Engineering Australia for giving me a chance to discuss my topic with a wider audience. This is my first ever speaking experience at a conference, and until now, I'm overwhelmed by the privilege of being here in front of everyone. Before we start, I would like to acknowledge the traditional owners of the land on which we gathered today for this presentation, the Wurundjeri people of the Kulin Nation here in East Melbourne, and the Ugambi people of the Gold Coast where I live and work. I pay my respects to their elders past, present, and emerging, and extend that respect to all Aboriginal and Torres Strait Islander peoples here today. To begin, let's talk about what we mean by transient events in water systems. One of the most well-known examples of a transient event is water hammer. This happens when there's a sudden change in the flow of water and often triggered by events such as the sudden shutdown of a pump, the rapid closure of a valve, or power failure. When the water's motion is interrupted, it creates a pressure surge that travels through the system. Transient events like water hammer can lead to significant stress on the infrastructure of the system and can potentially damage pipes, pumps, valves, and other critical components. These surges can lead to pipe bursts, joint failures, or leaks. In some cases, these failures can cause entire section of a distribution system to go offline, leading to costly repairs, water loss, and service interruptions. This is why understanding and managing transients is so critical in the design and operation of water systems. To elaborate further about water hammer in this video, pump failure in an unprotected system causes water to stop suddenly, leading to column separation. As the water flow stops, it creates a full vacuum in the pipeline, followed by a pressure bounce back which can produce high pressure surges. The surges can collapse the pipe due to the sudden pressure changes. However, in a system equipped with surge protection, such as an air valve, during a pump trip, the valve introduces air into the system. This air cushions the water column, maintaining pressure and preventing vacuum formation and reducing the risk of pipe collapse by mitigating the pressure surges. Water hammer isn't just a theoretical problem, it has a very real and tangible impacts on water systems. One of the most immediate consequences of water hammer is pipe bursts. The sudden pressure spike that results from a transient event can cause pipes to rupture, leading to significant water loss, property damage, and expensive repairs. Pumps and valves are at risk when rapid changes in pressure occur. Pumps can experience cavitation or even complete failure if they are subjected to significant pressure variations. For everyone's information, cavitation occurs when the pressure drops below the vapor pressure, causing vapor bubbles to form and collapse, potentially damaging the pipeline. Repeated transient events can lead to fatigue in system components. Even if a single event doesn't cause immediate failure, the accumulation of stress from multiple events can shorten the lifespan of the infrastructure. Today's presentation aims to explore a systems engineering approach to transient analysis in water distribution systems. My goal is to show how integrating systems engineering principles into the design and analysis process can help us manage the complexity of modern water systems more effectively. We will be using Bentley OpenFlows Hammer, a powerful software tool for modeling and simulating transient events in water systems. Unfortunately, this software is not free, but it is one of the useful applications engineers use in hydraulic modeling. I'll demonstrate how this tool can be used to create models that simulate transient events and will allow us to test different scenarios and identify potential issues in the system. Due to limited time, I will not be presenting a step-by-step procedure on how to create the model. Please let me know if you want a copy of the tutorial on how to use Bentley Hammer. The goal is that by the end of this session, I hope to convey how a systems engineering approach not only improves the efficiency of the design process, but also enhances the overall resilience and performance of the water distribution system. We will also look at how this approach helps streamline the identification and mitigation of risk, particularly in the context of transient events like water hammer. Let's take a moment to understand the physics behind water hammer. The Joukowsky equation is often used to calculate the pressure rise during a transient event, such as sudden stop in water flow. The equation is named after the famous Russian scientist and engineer Nikolai Igorovich Joukowsky, also known for his noble work in aerodynamics and hydrodynamics. The equation change of pressure equals to density multiplied by the speed of sound or wave speed multiplied by the change in the velocity. Don't worry, everyone, we will not be doing any manual calculations today. This equation provides a fundamental understanding of how pressure surges occur, particularly in simple systems. For example, if a valve closes rapidly, the flow of water is suddenly stopped, causing a spike in pressure that travels back through the system. This is where water hammer gets its name. The pressure surge can literally sound like a hammer hitting the pipe. However, while the Joukowsky equation is a useful starting point, it has its limitations. In a complex system, the presence of multiple transient events happening simultaneously or in rapid succession can complicate the dynamics of the system. This is where tools like Bentley Hammer come in, allowing us to model these complexities and gain a more accurate picture of how the system will behave during the transient events. Let's take a look at how Bentley OpenFlows Hammer works in practice. In this screenshot, we have simple water distribution system consisting of a single pump and two reservoirs. Simple systems like this can also be calculated using the Joukowsky equation. The pump draws water from the first reservoir and delivers it to the second through a pipeline. This setup represents a common type of water distribution network, and it's a good starting point for understanding how transient events affect the system. When we simulate this system in Bentley OpenFlows Hammer, we can observe the effects of different operational scenarios such as sudden pump shutdown or rapid valve closure. Bentley Hammer allows us to see how pressure and flow rates change through the system, and it provides us with data that we can use to make informed design decisions. Now, let's move on to a more complex system. In real-world applications, water distribution networks often consist of multiple pumps, valves, reservoirs, and pipelines, all working together to deliver water across large distances and varying elevations. These systems can be quite intricate, with many interdependent components that influence how the system responds to transient events. In this screenshot, we have a pump system with several branches feeding different parts of a water distribution network. The complexity of this system makes it more challenging to predict how it will react to transient events. For instance, a pump failure might cause pressure fluctuations through the entire network. Bentley Hammer allow us to model this complexity and simulate a wide range of scenarios and will help us identify potential weaknesses and design appropriate protections such as surge tanks, air valves, or pressure relief valves. Traditionally, the transient analysis process involves a series of steps that engineers follow to evaluate the effect of transient events on a water distribution system. In the design of pumping station, for example, these steps include defining the problem, setting up the model, simulating the transient event, analyzing the results, and then implementing a solution. While this approach can be effective, it can also has its limitations, especially when dealing with more complex systems. In today's water systems, the complexity and scale of the networks require a more structured approach to managing transient events. This is where systems engineering comes into play. So, in the traditional approach to transient analysis, several key problems are often encountered, especially as the complexity of the system increases. Let's go over some of the main issues that are based on my experience and experience from other engineers. First is increased error. When modeling complex systems, for example, human error is inevitable, particularly during repetitive manual tasks. The more components and scenarios you have, the greater the chance of making mistakes. Simple oversight in defining a boundary condition or selecting an input parameter can lead to inaccurate results and poor decision making. The second is poor risk management. Another common challenge in transient analysis is that risk is not always fully accounted for. The traditional approach may not incorporate systematic risk analysis techniques such as failure modes and effect analysis, or sometimes called FMEA, which can lead to errors in the design that are only discovered after a failure occurs. Now, let's explore how systems engineering approach can solve many of the problems we've just discussed. Systems engineering is a structured methodology that focuses on viewing the system as a whole. I have highlighted in red the improvements that we can incorporate or integrate into our traditional approach. First, in systems engineering, the first step is clearly defining the problem while involving all relevant stakeholders. It could be either engineers, operators, regulatory bodies, and even the community. This helps ensure that all the requirements of the system are well understood from the start. Second is instead of setting up isolated models, systems engineering encourages the creation of a holistic system model that takes into account the interactions between different components. If we understand how each part of the system interacts with others, we can simulate more realistic transient events and better predict their impacts. The third is a systems engineering approach involves extensive scenario testing and sensitivity analysis rather than just simulating few scenarios. This will allow us to test the system under a wide range of conditions from normal operating operations to extreme failure events and will provide a complete picture of the system's behavior. And the fourth, in systems engineering, analyzing the result isn't just about looking at the numbers. We can introduce risk management techniques like failure modes and effect analysis, as I mentioned earlier, to systematically identify potential failure points and assess the likelihood and impact of different risks. And then once a solution is implemented, systems engineering encourages continuous monitoring and feedback. I highly recommend this to ensure that the system remains resilient over time, even as conditions change. Lastly, in a systems engineering approach, verification and validation are an ongoing process. The system is continually tested against the original requirements, and adjustments are made as needed to ensure that it continues to meet performance standards. My apologies for my image. One of the text there is covered with my video. Now let's introduce the V diagram. The V diagram is a popular model in systems engineering, and it perfectly illustrates how the approach works in practice. Let's walk through it. On the left side of the diagram, we start with requirements definition and concept of operations. This is where we define the objectives, identify stakeholders, and establish baseline requirements for the system. As we move down to the left side, excuse me, we go through the high-level design and detailed design phases, where the water distribution system is designed both conceptually and in detail. At this point, we're focusing on the architecture of the system and how individual components will work together. At the bottom of the diagram, we reach the implementation phase where the design is turned into a working system. This is the bridge between the design and testing. Moving up the right side of the diagram, we start with unit testing followed by integration testing, where we test the interaction between components. Finally, we reach the top right side with system testing and acceptance testing, where the entire system is tested as a whole to ensure it meets the original requirements. So let's apply this concept in our sample design network. All right, so first activity for our work is a simple water transfer system. So the problem is a group of engineers and designers was tasked to design a water transfer system equipped with a pump station upstream. The water will be drawn from a nearby reservoir along a dedicated transmission pipeline to a downstream reservoir. The client has asked to prepare a high-level engineering process breakdown of the proposed design and construction of the water transfer system. In our first activity, I'd like to request everyone to follow the instruction. So all you need to do is you can scan the QR code or visit the link, and you have 10 minutes to finish this challenge. So once you follow the link or scan the QR code, it will present you with this word wall screen, and all you need to do is just to enter your name. Once you are in word wall, all you need to do is just to drag that little circle of each of these activities to appropriate um, V diagram process. And then at the end, once you finish, you will see your score, whether you did it right or you did it wrong. There's no grade, so don't worry about making mistakes. So here we have a simple water transfer systems that we will be using as a case study. This system consists of a water pumping station that draws water from a nearby reservoir. The normal water level is 383 meters. The water is then conveyed at a rate of 468 liters per second through a dedicated transmission pipeline to a second reservoir, which has a normal water level of 456 meters. Pump is located at an elevation of 363 meters, operating at 1,760 revolutions per minute. This is a fairly common configuration in water distribution networks, and it provides a good example of how transient events, such as pump shutdown, can affect the system. This part of the presentation is supposed to be showing you how to use the Bentley Hammer software, but because of our limited time, we are going to skip this one. So now we are going to follow our V diagram to analyze our water distribution network. The concept of operations or ConOps is a critical part of the systems engineering approach. This phase is all about defining what the system needs to do and how it will operate under normal and extreme conditions. So the first is to define the objective. In our sample, the objective is to ensure the reliable and efficient delivery of water from one reservoir to another. And also the system must be able to handle pressure surges without damaging the infrastructure. The second is identify stakeholders and requirements. The stakeholders in this scenario include water utility company that operates the system, the engineers who design and maintain it, and the end users who rely on it for a consistent water supply. Each of these stakeholders has different requirements: operational efficiency, system resilience, and regulatory compliance that need to be considered in the design. Establish the baseline means we are setting the initial conditions for the system. This includes knowing the normal operating parameters like flow rates, pressures, and water levels, as well as the conditions under which the system is expected to fail or operate under stress. Once the concept of operations is established, we move on to defining the system's requirements, and we have identified three system requirements. First is the functional requirements, which include the specific tasks the system needs to perform. For example, the system must be able to deliver 468 liters per second from one reservoir to the other. Another functional requirements include minimizing pressure spikes, maintaining flow stability, and preventing component failure. The second is the regulatory constraints. So water systems must also comply with a range of regulatory standards related to safety, environmental protection, and operational efficiency. In our case, this might include compliance with local water management regulations and safety standards designed to prevent over-pressurization and system failure. The last one is the design constraints. These are the limitations imposed on the system by factors like budget, space, and available technology. For example, we might have constraints on the size or location of the protective components, like surge tanks or pressure relief valves. Design constraints also include any limits on the types of materials used, the energy efficiency of the system, and the expected lifespan of the components. In the high-level design phase, we focus on the overall architecture of the water transfer system and its key components. The aim here is to establish how the system will function as a whole, while still leaving room for detailed design work later. The hydraulic network design, at this stage, we create a basic layout of the hydraulic network, including the pipelines, pumps, and reservoirs. We define the connections between these components and consider how the system will operate under normal and transient conditions. In this network design, you can see different types of protection devices being modeled to see how the system performs using various scenarios. The transient scenarios, we identify the key transient scenarios that we'll need to simulate during testing. This might include pump shutdowns, rapid valve closures, or power failures. In this case, we will be using a pump shutdown or pump trip event. Once we've completed the high-level design, we move into the detailed design phase. This is where we get into the specifics of how the system will be built and how it will respond to transient events. The data input, in this stage, we enter detailed data into the model, such as pipe length, diameters, roughness coefficients, pump curves, and valve characteristics. In Bentley Hammer, this is where we also set boundary conditions and define the initial water levels, pressure, and flow rates. In transient control components, we introduce components specifically designed to manage transients, such as surge tanks, hydropneumatic tanks, and air valves. We'll place these components strategically throughout the network to ensure they provide protection where it's most needed. Finally, we define the simulation parameters for our transient analysis. This includes specifying the types of transient events we want to simulate, such as pump failure or valve closures, as well as the time steps and duration for the simulation. In Bentley Hammer, we can simulate these events and monitor how the system responds in real time and observe key metrics like pressure, velocity, and flow rate changes. Now that we've completed the detailed design, we move into the implementation phase where we actually run the simulation and analysis of the results. In the model simulation, at this point, we input all the data from the detailed design phase into Bentley Hammer and run the simulation. This allows us to see how the system performs under different transient scenarios. In our example, we simulate a pump shutdown and observe how the pressure and flow change throughout the system. We simulate both the unprotected and protected systems. And then we have the initial results. So the initial results from the simulations give us a snapshot of the system's behavior during a transient event. We'll look for any pressure spikes, cavitation, or other issues that could indicate a potential failure point in the system. These results are critical for identifying areas where the design may need to be adjusted or where additional protection might be required. Here we have the model of the water distribution system without any protective components in place. In this scenario, we simulate a pump shutdown and observe the effects of this resulting water hammer. In real systems, this kind of unprotected scenario could lead to pipe burst, valve failures, and pump damage, particularly in areas where the pressure spike exceeds the design limits of the components. So after running the simulation of the unprotected system, so we have here the animation of the hydraulic rate line and the air vapor volume. This is a good thing about Bentley Hammer is you can generate like an animation to see the behavior of the pressure. So let's have a look. The red line, by the way, is the hydraulic rate line, and on the top graph, the red line is actually the air vapor volume. So you can see during the pump shutdown how the trend of the pressure is propagating in the system. There's a lot of spikes, which we don't want in our system. All right, let's post this and we will move forward. Next, we introduce a hydropneumatic tank into the system as a protective measure. Hydropneumatic tanks are commonly used in water distribution networks to absorb pressure surges and prevent water hammer from causing damage. In this model, we place the tank near the pump where the pressure spikes are most severe. Adding this protection, we can control the pressure fluctuations more effectively. The hydropneumatic tank allows excess pressure to be absorbed when the pump shuts down, preventing the pressure from rising too quickly and reducing the risk of system damage. Here are the results after introducing the hydropneumatic tank. So let's play. As you can see, the pressure spikes have been significantly reduced compared to the unprotected model. The tank absorbs much of the excess pressure, allowing the system to handle the pump shutdown without exceeding safe pressure limits. This demonstrates the effectiveness of using protective components like hydropneumatic tanks in mitigating the effects of transient events. When we run these simulations in Bentley Hammer, we can fine-tune the design of these protective measures to ensure they provide the necessary level of protection without being over-engineered. So, once we've implemented the necessary protections, the next step is to transition to the testing and evaluation phase. This is where we verify that the system performs as expected under both normal operating conditions and transient events. Moving from component validation to system level validation, it's important to test each component on its own, but we also need to ensure that all components work together as a cohesive system. This means testing the interaction between pumps, valves, surge tanks, and pipelines to ensure they respond appropriately to transient events. Purpose of testing is to ensure the system behaves as expected and meets the initial design requirements. If any issues are identified during testing, we can make adjustments before moving on to the final implementation. In the unit testing phase, we test the individual components of the system to ensure they meet the design specifications and perform reliably under different conditions. Like for example, the pipes, we test the integrity of the pipelines to ensure they can handle the pressure fluctuations caused by transient events. This includes verifying that the pipe material, diameter, and thickness are adequate for the expected pressures. For the pumps, we test them to ensure they operate efficiently under normal conditions and respond appropriately to shutdowns and other transient events. We'll also verify the pump's protection systems, such as check valves or surge tanks, functions as intended. In the valves, we test them. We test their performance to ensure they open and close smoothly and that they can handle rapid changes in flow without causing pressure spikes. And then we test the surge tanks to verify that they absorb pressure surges effectively and prevent water hammer from damaging the system. This includes checking the sizing and placement of the tanks to ensure they provide the right level of protection. And then lastly, our reservoir. We test the reservoir to ensure they maintain appropriate water levels and can accommodate the flow rates specified in the design. The interaction between the reservoir and other components like pumps and pipelines is also tested to ensure smooth operation. After unit testing, we move on to integration testing where we focus on how the individual components interact with one another within the system. Component interaction is about integration testing and ensure that the pumps, valves, surge tanks, and pipelines work together as a unified system. Even if each component performs well on its own, issues can arise when they are combined. For example, a valve might behave differently when installed in a system with fluctuating pressures, or a pump might interact with a surge tank in unexpected ways. In the network behavior phase, we simulate various operating conditions to observe how the entire network behaves. Well, look for any signs of unexpected pressure fluctuations, flow reversals, or other anomalies that could indicate problems with the system design. If any issues are identified during the integration testing, we can make adjustments to the system. This might involve like resizing a component, changing the location of a surge tank, or adjusting the operating parameters of a pump. The goal is to ensure that the entire system operates smoothly and reliably. So here is an example of how we can do integration testing in transient analysis. We set up time history and locate a point in the system where you want to see the pressure behavior at that point. In this case, we use the location from pump 1 to pump 1 discharge. Then we run the simulations using both protected and unprotected. In this image, you can see that without the surge protection, we can see an aggressive wavefront, fluctuation in flow of water, and some air pockets formation. With the surge protection, on the other hand, we can see a smooth transition of pressure at long intervals, and we did not see any fluctuations in water flow or air pocket formation. So from this, we can say that our hydropneumatic tank is performing as it should be. System testing is the final phase of testing where we simulate the performance of the entire water distribution network under both normal and transient conditions. In system testing, we run end-to-end simulation to observe the behavior of the entire network during typical operations and during transient events. This gives us a complete picture of how the system performs as a whole. And then we verify that the system meets the performance criteria established during this design phase. This includes checking that the system can handle expected flow rates, pressure ranges, and transient events without exceeding safe operating limits. And then finally, we ensure that the system complies with all regulatory and safety requirements. This includes verifying that the system operates within the pressure and flow limits specified by the local water authorities and that all components are designed to withstand transient events without failure. Acceptance testing is the last step before the system is fully deployed. So this phase involves validating the system against real-world data and ensuring that it meets the expectations of stakeholders. In acceptance testing, we use real-world data from similar water systems or actual field measurements to fine-tune the model. This will help us to see if the system behaves as expected under real operating conditions. This stage, we can check with the client or water utilities some similar network design and if there are any transient events in the past that we can compare with. We also conduct a stakeholder review to ensure that the system meets their needs and requirements. This might include verifying that the system is cost effective, easy to maintain, and resilient to transient events. If any final adjustments are needed, we make them during the acceptance testing phase. Once all parties are satisfied, the system is ready for implementation. Now we're getting there. So this is our final activity for this workshop, which is the Smart Irrigation System Challenge. So again, please follow the instruction and you can use the QR code to log in into WordWall and join the activity. Um, Again, you will be presented with a screen like this where you can enter your name. And then you will be presented with a series of activities. I think this is not, the level is not really difficult. I think this is like average. So you can just drag the activity to specific testing purposes. And then at the end, you will see whether you get it right or wrong. And again, don't feel pressured about this activity. This is just to learn how we can identify um, like what's involved in the testing process. So we are almost done with this session. So throughout this process, we've learned several key lessons that can help improve future projects. Let's summarize these lessons and discuss some best practices for transient analysis. The first one is the early stakeholder involvement ensures alignment and clarity. So this process, early process can ensure that everyone is aligned on the system's objectives and requirements. And this reduces the likelihood of misunderstanding or scope changes later on. Testing at all levels, like unit integration and system, is critical for identifying potential issues before they become costly problems. Simulating a wide range of scenarios can ensure that the system is resilient and capable of handling extreme conditions. Validating the model against real-world data can improve the simulation's accuracy and ensure that the system performs as expected in the field. This is particularly important for transient events, which can behave unpredictably in real-world systems. I guess that was all about it for today. Thank you all for your time. I hope you found this presentation on systems engineering and transient analysis useful. If you'd like to stay connected or have any further questions, please feel free to contact me via LinkedIn. I'll be happy to discuss any questions or ideas you might have about transient analysis, systems engineering, or Bentley Hammer. Let's keep in touch and continue the conversation about building better, more resilient water systems. Thanks again.